In this video, we are going to explore our knowledge of the atomic level interactions to explain how helium changes states of matter. Let's begin by drawing a picture of what you imagine solid helium looks like. Go ahead and pause the video and draw what you think helium would look like as a solid on the atomic or molecular scale. Here is a textbook image of what helium looks like as a solid. However, you might have drawn something like the number 1 here. The image shown has a student's depiction of what solid, liquid, and gaseous helium looks like on the atomic level. Here are 2 more samples. Your image may look something more like one of these variations. Each of these drawings have some characteristics that match our evidence for what helium should look like as a solid, liquid, and gas. However, as you can see in the variations here, envisioning these helium atoms in each state of matter can be quite difficult. Let's begin our look into how helium changes states of matter with a quick recap of Coulomb's law. Remember that Coulomb's law states that like charges attract and unlike charges repel each other. If needed, we could draw potential energy diagrams for 2 like charges and for 2 unlike charges to model the electrostatic interactions between helium atoms. If you would like a review of these potential energy diagrams, remember that we modeled a few in a previous video from this unit. The GIF here shows that as helium atoms move closer to one another, the kinetic energy increases and the potential energy decreases. However, remember that if the 2 atoms get too close to one another, the like charges from their electron clouds will repel one another, causing a dramatic increase in potential energy. Let's use our model of the atom to look closer into this relationship. Remember, our model of the atom has a tiny, dense nucleus surrounded by a cloud of electrons. You can think of that cloud as being fluffy or amorphous. On average, it is a spherical cloud, but it can fluctuate momentarily, causing the electron density to be distorted at any given moment. Everything in chemistry depends on this fluctuation. So we've reviewed that atoms may attract or repel each other. The amount that they attract or repel each other is dependent not only upon their charge, but also their proximity to one another. This means we need some way to describe how the atom's changes in location could affect their electrostatic interactions, the attraction or repulsion between atoms. For this, we will dive a little deeper into thermal energy and temperature. We can first just ask, what is thermal energy? And what is temperature? And even, what is the relationship between thermal energy and temperature? These questions will help us better explain how and why helium changes states of matter. To begin, thermal energy is the measure of the total kinetic energy of the particles in a sample. Notice that not all atoms in a sample will have the same kinetic energy. However, thermal energy is the total of all kinetic energies for every particle in a sample. Alternatively, temperature is the average kinetic energy of all particles in a sample. Remember again that not all atoms will have the same kinetic energy. However, temperature will describe the average kinetic energy of the particles in that sample. Consider the example here from Bill Nye. In the picture is a large ice sculpture of a swan, and Bill is holding a lit match. The match has a higher temperature than the ice sculpture. You can feel this difference from touching each the match and the ice sculpture, but be careful not to burn your hands. However, the ice sculpture has more thermal energy than the match. The ice sculpture has a higher thermal energy than the match because there are more particles making up the ice sculpture. Each particle in the ice sculpture has a very small amount of kinetic energy, and if we sum up the kinetic energy of all the particles in the ice sculpture, it will be greater than that of the match, which arguably has fewer particles, but those fewer particles are at a higher kinetic energy. Let's relate these ideas back to our helium atoms. What happens when thermal energy is added to helium atoms that are in the solid state? Well, first, the kinetic energy of the atoms will increase. The helium atoms will move faster by moving, colliding, or vibrating with more energy. This increase in kinetic energy would probably result in an increase in temperature. We'll talk more later about why this isn't necessarily guaranteed. But if we are increasing the thermal energy, we are increasing the kinetic energy of the particles. As the average kinetic energy increases, so too will the temperature. Eventually, the atoms vibrate strongly enough and have enough kinetic energy to overcome the attractive force between the two helium atoms, and they'll fly apart. This process could overall result in a change in state of the helium atoms, from something of lower energy to a state with higher energy. To see this in action, check out the video provided here. In this video, water molecules gradually have heat applied to them, increasing their kinetic energy until they eventually overcome the electrostatic interactions holding them in place, and they change from a solid state of matter into a liquid state of matter.